Hello and welcome again to my channel. I want to show you today the details the details of this tutorial we made earlier on the other channel. So in this tutorial here, we've built an Arduino based RF transmitter and receiver. We're going to use this transmitter and receiver to send data from one end to the other, obviously. But as you can see on the screen right there, there's the Arduino here. Let me highlight it. There's the Arduino. We're using Arduino Uno for now, and then we're just using one input output pin, and then one analog pin, analog input, and then one digital input output pin for the output. So basically we're using a total of two input output pins to achieve what we're doing here. Now the resistor network we have here is only limited to your imagination or the size of memory on your microcontroller. In this case, we're using an Arduino Uno, so you can have many more lines of codes here, so your number of buttons can actually increase. So here we have switches 1, 2, 3, 4, 5, and to increase that, you can see that the network basically it's resistor and switch, resistor and switch, resistor and switch. So you can build this yourself. You can extend this as much as you want. We'll show you in the code how we're able to do that. And then here is the base resistor. Here we have this resistor from the analog inputs to ground, and then we have the other resistor network sent from the power supply, which is this positive here. And as we close the switches, so this will be S1, S2, S3, S4, S5. As you close the switches, you're increasing, you're adding up the resistances. So when you close S1, the Arduino will measure only so let's just call this R1. So give you the value of R1 alone. Then when I close S2, it will give you R1 plus R2. Then this is R3, R4, R5. So this let's just call this RB. Let's not include it in the number. Or Rin. Let's call it Rin. We'll not include it in numbering so that we don't run out of numbers. If you want to add more resistors, you just keep adding to the going to your left. Just keep adding resistors and switches. So when I close S1, then when I close S1, the resistor will the Arduino will just read R1. When I close S2, the Arduino will read R1 plus R2. And when I close SN, then the Arduino will read R1 plus R2 all the way to plus Rn. So that's the way we'll read it and then add it up. So we're using the same value of resistor. So in this case, if I close S1 and then close S2 at the same time, it doesn't really matter. The Arduino only knows about S1 because S1 goes down here. So only one switch at a time. If you want to get a different function when you press two buttons, then you have to have a different configuration, because once you close S1, let's assume the voltage is flowing or the current is flowing from here. It closes this way. Let's use yellow. So if current is flowing this way, conventional current just goes this path, right? So, and it will ignore the rest of the switches. So you have to close one switch at a time. Now we're going to show you the code and how the Arduino was able to determine this. And then based on the value, write a code that tells it when you get this value, this is what I want you to do. Okay, so let's go to the codes and just analyze that quickly. Right, so here is the code here. So we declare this int analog A1, analog pin A1, and really this is just A1, so ignore this. It was initially written for 80 tiny. That's why you see that. And then this one is just pin 8, pin number 8. It was initially written for 80 tiny, but because we want you to see what happens when we press a button on the serial monitor, we had changed the code slightly. So the resistor R1 is 2K, and then R2 it's 0 for now, and then we'll declare this float buffer is 0. So in the setup, in the void setup, we started the serial again because we want to show something on the serial monitor, and then we'll declare 2 pin modes. So data out is the output and control is the input. All right, so in the void loop, we want to find the control value. Remember here there's a variable we declared as control value, int value. Control value is 0, right? So we're saying in the void loop, control value is analog read of control pin. So we read the value there, and we say if that value is greater than 100. Sometimes you get some jitters and some random values without you closing a button. So we found out that that value is always less than 100. So we declared to say if it is more than 100, then you can go ahead and do any other thing. For debugging purposes, we were printing it out before we wrote the rest of the codes. So normally when you do this, you want to check quickly. You don't want to write the whole codes and find out there was an issue. So we printed out the value. Whatever we read, we printed it out to make sure that it's working. And then that value was nowhere near the value we were looking for. It was nowhere near 2000, and we know that it's 2000 ohms or 2 kilo ohms on the board. So what we did, we used this formula. We'll learn this from other people. We'll use this formula to determine the value of R2. And once the value of R2 is determined, then we're saying if that value, so we printed it out first. Again, before we proceeded, we printed it out to make sure that it's close to what we wanted. And this value, based on what we printed out here, we wrote these codes. We found out that sometimes when you close the resistor, the value, when you close the switch, the value sometimes could be somewhere around 2000 or slightly more than 2000. It can be up to 2400. Like in this case, the first button we pressed was giving us a value of 2096, which is close. 2 kilo ohms is close because of its tolerance, but if I press it multiple times, I might not get the same value. So now I'm getting 2200. Press it again, 2100. So this is why we decided to give a range for the first value, and as long as it is less than the second value, because we know the second value is going to be 4 kilo ohms, so as long as it's less than that, we'll just call that the first switch. Right now, if you're going to do multiple switches, which means 2 resistors can combine and give you a new value, you know that resistors in parallel will tend towards the smaller value, and resistors in series we add. We talked about this in the basic electronics tutorials, but let's just do it one more time here. So if I have a resistor and another resistor in parallel, the effective resistance of this, or the equivalent resistance of this, will tend towards the smaller of the two. So if I have, let's say, 20k here and I have 10k here, this value will tend towards 10k. It will be greater than 10k, it will be less than 10k, but it will tend towards 10k. So the actual value will be 1 over, so if you call this R1 and call this R2, and then you call this R equivalent, so R equivalent will be equal to 1 over R1 plus R2. So in this case, R equivalent will be equal to R1 plus R2 over R1 R2. So then that means 10 plus 20 over 10. I just summed that up instead of over 10 times 20. So this would be 30K divided by 200K. Right, so all right, let's make sure we got this value correctly. And times 1000. All right, so I think we're making gross assumption here. This is 10. Let's just do this one more time. So okay, so there's a mistake in the formula. There's a mistake in the formula. The formula should be 1 over. Yeah, so there's a mistake here. 1 over R equivalent is that. And so to solve this, then we go R1 plus R2. R1 times R2. So that when you divide this, you get R2 plus R1. All right. So 1 over R equivalent is that. Such that R equivalent, that's where we made a mistake. So that R equivalent is now R1, R2 over R1 plus R2. So the initial calculation was supposed to be still 1 over R equivalent. Yeah, so that was a mistake that we made earlier. So it should still be 1 over. All right. So in that case, then we're talking about 20 times 10 over 20 plus 10. And this will be 200 over 30. So when you do that, you're getting something close to 6. Remember, don't forget the K. It's just to say 1,000. So you'll be getting something like 6.6 kilo ohms. So if you're using resistors in parallel, if you're using resistors in parallel, as we established here, the value will tend towards the lesser one, but it will be less than that. It will be less than the least if they're in parallel. Now for resistors in series, so if I have one resistor, let's make sure we draw it, the symbol very well. So, and another resistor, but in this case they're in series. So R1 and R2, such that the equivalent, R equivalent, will just be R1 plus R2. So R1 plus R2. So that's the case we're using today, so that if you have R1 as 2K and R2 as 2K, your R equivalent is going to be 4K. So that's just what we've demonstrated today. Okay. So in our case, let's go back to the circuit. In our case, we have 2K resistors all in series. So as you add up, as you go from S1 to S5, as you add up, the values of the resistance will increase. So that is what the Arduino is reading. Now, if you want to have multiple switches pressed at the same time, you have to have a different way of configuring the switch so that the resistors can be added in parallel. The configuration we have here is a series combination. And to do that in parallel is not really hard. So let's just give an example. Let's give a circuit example. So for a circuit example for that, let's link this up to, let's draw. Okay. So let's draw a shape here for the Arduino. Right. So let's just pretend that's the Arduino, and we want to have the same connection, but we want this to be in parallel. So this is what we're going to do. We're going to have each resistor independent of the other. And so on and so forth. And then we're going to have our switches here. All right, and this will go to an analog input, and then obviously the R, what did we call that? R in. Yeah, obviously our R in will just go from here to ground then. This will be R in. So this will be R1, R2, R3, R4, and so on in that direction. This will be our positive, and this will be the Arduino. Or you can just call it microcontroller. So that's your microcontroller right there. So when you close S1, then if this is our S1, S2, S3, and S4. So when you close S1, for instance, the Arduino will just read the value of R1. When you close S2, will read S2, you will read R2. When you close S3, will read R3. S4 will read R4, and so on and so forth. So let's just put dots here and put another resistor and another switch. Let's call that switch SN, and this will be RN. So as you go in that direction, let's make this dotted so that it just shows it continues to that point. Now, if I close two switches, then if I close S1 and S2, the Arduino will be reading the value of S1 and S2. If I close S1, S2, S3, it will be reading the value of S1, S2, S3 equivalent. If I close all switches, it will be reading the value of all switches. So you write your code. We're going to look at the code now. But if you're using this combination, so this will be parallel design. So call this parallel design. And the one we're working on today is a series design. So there's a series and there's a parallel design. So everything you've learned in school about resistors in series and in parallel, you can call them up here and use that formula to determine what values of resistors to use to give you specific values. So remember, as you close the switches, the values will be computed, right? For the parallel design, you have to bear in mind that R, and don't make the mistake we made earlier on. We forgot about the 1 over. Don't forget that. It starts with 1 over. R equivalent, right, is equal to 1 over R1 plus 1 over R2 plus, for lack of space, I'm just going to put my dots, and then 1 over Rn. That's how you get your equivalent. Let's change something here. Let's put this in a box. All right. So if you want to get the R equivalent, this is the formula you use. So you choose the resistors wisely. When you choose these resistors, you choose them wisely. The reason being, if you close multiple switches, you can get different values. And if you're not very careful in your choices, you might get a value that is so close to another one that the Arduino might think you have performed that function while you have performed a different function. Also note, if you have all the resistors as the same value, two resistors in parallel, and they have the same value, then the equivalent resistance will be equal to one of them. For instance, in this case we have 2 kilo ohms, 2 kilo ohm resistors. If we have two of them in parallel, the equivalent will be half of one of them. So let's see. So if you have 1 over R equivalent, we're saying that value, we want to find that from 2 kilo ohms, 1 over 2 kilo ohms. So basically, this will give us R equivalent will be equal to 2k times 2k divided by 2k plus 2k. So that means this will be 4k divided by 4k. So then this value will be 1k. So when you have two resistors of equal values in parallel, the equivalent resistance is just half of one of them. If you have them in series, then the equivalent resistance is the sum of both of them. So you can, if you're using a series combination that we looked at earlier, you find out that if you close switch number 2, you'll be getting 4 kilo ohms. So let's just press it on this board here and show on our serial monitor what happens. And we're going to show you the circuit also. Let's just show you the circuit, and we'll clear this. And so there's S1, that's S2. When I press S2, you see on the serial monitor, it says second button value 4,500. Now really it could be any value from 4,000, because I'll show you also the code. You see what we wrote there. You see 4,300, 4,400, and so on and so forth. So let's look at the code, what we did for second button. So for second button, we said if the value is from 3,900 to 5,000, that's a wide range. So just tell us we've pressed the second button. Again, we can do this and give it a wide range because we actually know the values of the resistors on the board. They are all 2 kilo ohms each. So we know by the time you press the second button, you can only get a maximum of 4,000 plus the tolerance. So even if it's 20% tolerance, so you're just going to get the value plus the value of the tolerance. So that's what we did right there. And then also the third button, fourth button, fifth button, and so on and so forth. So we wrote that code for third button, and we said if it's between this range and that range, we know in practical sense we should get around 6 kilo ohms. So we just went a little bit lower, and then 1,000 ohms higher. So that's for the third button. And then we did the same thing for the fourth button. We know the value should be 8,000, but anything maybe slightly smaller or slightly bigger, but as long as it's less than 10, because we know the next one will give us 10,000. So that's how we wrote these codes. And then when that happens, we say call this function. Call the function. This function is a signal generator, and the signal generator is generating a square wave in with this delay in it. So this delay is, let's just show the code we wrote for that. So there's a this code we wrote here, and it has a timeout, and the timeout is the value that we put in this parenthesis here. So this is the microseconds timeout. So it's going to generate a square wave that first of all it will go high and stay on for this timeout period, which is 12,000 microseconds, and then it will send it to low and then do the same timeout. And if the button is still held, it will repeat. Otherwise, it will just do that, and there will be a delay of a second, and then the process will be available for you to press another button. Because again, if you release the button and the condition is no longer true, so it will not be in that loop. That's why when you press it, you get that happen. And I can show you the, let's just do that one more time. You can see the LEDs are flashing, the transmitter is flashing, at the same time the receiver is flashing. If the LED is shaking, okay, yeah. One of the things to avoid, to look out for when you're using breadboards is that sometimes the components are shaky. That's why I had to bend these ones down to make sure that they get good connection. I had issues when I was setting it up, and I figured that some of the pins were not, especially for the switches, some of the pins were not connecting properly. So I had to find a creative way of making them connect properly. But as I press the transmitter, this is the transmitter, so it sends the signal, and then the receiver gets that. That's the receiver. Now I can prove this. I can remove the transmitter from the board. If I remove it, this will only flash, but the receiver will not flash. Reason being, the signal is not being transferred, wirelessly. So you can see the LED blinks, on the transmitter side, but nothing happens on the receiver side. So what I'm gonna do right now is to show you how the I'm just gonna put the transmitter back. I'm gonna put the transmitter button back, the transmitter chipset back, and we'll work on this one more time. So let's put the transmitter back, and then when I press it, both the transmitter and the receiver will function as expected. Alright, so transmit, receive, transmit, and receive. Alright, so that's our receiver right there. So I can also do the same on the receiver side. I can remove the receiver from the board, and then just try to, yeah, the transmitter will work, but the receiver, the LED on the receive side will not work. Of course, goes without saying, right? So we're just gonna put it back. Alright, so that pin is VCC. Alright, we're gonna try it again. Yep, and it's working as it should again. Alright, so the transmitter and the receiver functions as we expect it to function, and you can see the serial monitor explaining to us or displaying to us which button has been pressed. Now you can build this yourself. In the next episode, that will be next weekend, we'll be showing you how to build the receive side. Right now, all we're displaying here is the fact that you can receive the signal, but there's no distinction to which button has been pressed. So in the next episode, we'll probably have to connect the maybe LEDs, multiple LEDs on the receive side to correspond with which button has been pressed. And the receiver alone cannot do that. We will have to have a microcontroller that will detect which one has been pressed. Now we can use an ATtiny. We'll show you the details of the circuit if we use ATtiny, but we can use an ATtiny with only 3 input-output pins to represent these 5 buttons. So we will do it like a logic gate. So you can have 3 inputs to represent 8 states. So let's say we have A, B, and C. And in terms of digital logic, we can have all zeros. We can have all zeros. Alright, so we're not getting the zeros to close. We can have all zeros, or we can have 2 zeros and a 1. Okay, we can have this way: 0 1 1, 1 0 0, 1 0 1, 1 1 0, and 1 1 1. So this should be 8 if you count it. So that would be 0 1 2 3 4 5 6 7. 0 to 7, that will give you 8. So we can have this condition, but we only have 5 switches here: 1 2 3 4 5. So in that case, we can use maybe from here to here. So 1 2 3 4 5. Okay, we can actually use more than we need. So we can use this 1 2 3 4 5. And the reason for this is we want to avoid all zeros, because we want it to start from all zeros. And then we can use any other combination, but we can just use from here, except the first entry. We can use the rest to indicate the state. So we can have 3 LEDs, and when this one is on, we know we've pressed number 1. when the middle LED is on, we know we've pressed number 2. When 2 are on, we know we've pressed number 3. And when we have the first LED on, we know we've pressed number 4, and so on and so forth. So we can use that to show what button has been pressed. And of course, this is just a proof of concept. You can then go ahead and use it for other things. You can use it to play music, use it to control toy cars, and so on and so forth. This is not the end of it. This is just the beginning, the introduction. But you can just go ahead and be creative and use it as you wish. Alright, so we're giving you more details here. And again, go to Hackernet and watch the videos there. Subscribe here and also on that channel if you have not done so already. If you have done so, thank you so much. If you have any video idea, any tutorial idea that you want us to make, please leave it in the comments. And the reason we're making this video, giving some details and so on and so forth, is some of the things that we've done before that we had challenges with, or we thought that people might have challenges with, we just show it. We've seen people who build similar things, but they use multiple input-output pins, and we thought you can do that with less input-output pins. And that's why we made this video. Not that you don't have other tutorials on this using multiple, other methods, but we thought with resistors being as cheap as they are and microcontrollers being also not too expensive, but the pins being limited, you can actually take resistors. You're going to use the switches anyway, so that is a constant, but you can take resistors and save space, save the number of pins that you use on your microcontrollers. All right. Now, if you have subscribed, again, thank you. If you have not, please do so right now. And please don't forget to like and share this video. Until we come your way again with more contents, stay enthused. Bye for now.